Today in plasma physics we are going to start a new topic, actually that is called fluid description of plasma. And this branch of plasma physics is also called Magnetohydrodynamics. Actually in Magnetohydrodynamics we study a set of equations which is called MHD equation. The full form is Magnetohydrodynamic equations. For your convenience, I will divide this topic in 3 lectures. So this is the first part of my lecture series of this topic. And before knowing what are MHD equations, I would like to just say something about magnetohydrodynamics. Actually, what is magnetohydrodynamics? We would like to understand it first, and after that we will discuss the MHD equations. So the main points I have mentioned here. Actually, as I have told you, this is fluid description of plasma, not particle description. And in the domain of magnetohydrodynamics, we treat plasma as a single component conducting fluid. And in such a fluid, there is no charge separation, and as there is no charge separation, so electrostatic forces do not come into the picture. And if such a conducting fluid is subjected to an external magnetic field, or you can say if such a conducting fluid flows through an external magnetic field, then an electric current is induced in the fluid, and this electric current will also produce magnetic field. So here there are 2 magnetic fields. First one is external magnetic field, in which our plasma fluid is moving, and due to the induction current, internal magnetic field is produced, and that internal magnetic field actually modify the motion of modify the field. As now there will be 2 fields, one is external field, and due to that external field an induced internal magnetic field is produced. So there will be just a combination of the 2 fields, and hence you can say the field gets modified. And you have definitely studied hydrodynamics. In hydrodynamics we study the motion of fluid, and as here in similar manner this conducting fluid is flowing. So definitely due to the motion of the conducting fluid, mechanical forces are also developed, and this mechanical force which are developed due to the motion of the fluid actually modify the motion of the fluid. Among these mechanical forces are so many forces which I will discuss when we will derive the MHD equation. These forces are basically gravitational force, you can say force due to collision, force due to pressure difference. These are mechanical forces, and these forces are the result of motion of the fluid, and such developed force actually modify the motion of the fluid. So here I have mentioned that mechanical forces modify the motion of the fluid. So what you see here, actually there are 2 types of phenomena taking place simultaneously. First one is actually electromagnetic phenomena, and another is just hydrodynamic motion of fluid. So in this case there is just a coupling of hydrodynamic motion and electromagnetic phenomena. And actually this coupling of hydrodynamic motion and electromagnetic phenomena is the subject matter of the magnetohydrodynamics. So as a definition you can say that magnetohydrodynamics is the study of interaction between the motion of plasma fluid and the field. So this is just a coupling or an interaction of motion of plasma fluid and the magnetic field, or you may simply field, there may be electric field too. So the study of the motion of conducting fluid in electric and magnetic field, that is electromagnetic field, is the subject matter of hydrodynamics, as I have told you. And so we are to utilize Maxwell's field equations together with the equations of hydrodynamics. As you know, whenever electromagnetic phenomena are described, our mathematical tools are what? Mathematical tools to describe the electromagnetic phenomena are Maxwell's field equations. So in this case, Maxwell's field equations are also known as MHD equations. And again, since it is simply a hydrodynamical motion, so the equations of hydrodynamics, that just like conservation principle of mass, that is equation of continuity, so all these equations comprise the MHD equations. And now I would like to derive the MHD equation. The first equation, which is the most important MHD equation, is known as momentum equation. I have just here written the momentum equation. This is written as del V by del T plus V dot del V equal to Q by M E plus V cross B minus nu C into V plus G minus gradient of P, that is del P over rho. In this equation, actually this V represents the average velocity of the plasma particles. Del, you know, this is gradient operator with respect to the space, and this Q by M, this is a specific charge of plasma particle, and separately you can say Q is charge of the particle and M is mass, and this ratio is called a specific charge of the plasma particle. E represents the electric field and B magnetic field. Here nu C is a constant which is called in fact collision constant. G is simply acceleration due to gravity, and P represents the pressure, and rho is density of the plasma fluid. So these are the meaning of different terms in this equation. So first of all, I would like to derive this very equation, but its derivation will be discussed in detail in 2 lectures. So first of all, we consider that our plasma fluid is subjected to an electromagnetic field. That is, an electric and magnetic field are present in the region where the plasma fluid is moving. And you know, if a charged body is in motion in an electromagnetic field, then the charged body experiences in fact Lorentz force, that is the resultant of electric and magnetic force, and that is called Lorentz force. So first of all, we consider that our plasma fluid is subjected only to electromagnetic field, and after that we will consider the different forces which will act on this conducting fluid. But first of all, we are going to consider only electromagnetic field as subject in which the plasma fluid is moving. So consider a plasma fluid moving in an electromagnetic field. No other field is present as I have considered, but definitely other fields will be also present, which I will consider later on. So When a charged particle, is in electromagnetic field, the net force acting on it is known as Lorentz force. And so, if we want to write the equation of motion of the charged particle, then the net force acting will be Lorentz force, and that will be equated to mass of the particle times acceleration of the particle. So let Q equal to charge of a plasma particle and m is mass of the same particle. Or in other words, you can say this Q over m is a specific charge of plasma particle. And for convenience, we assume that all particles of plasma have same this specific charge, that is Q over m. It means the specific charge of plasma particles are equal, and that is equal to Q by m, although they will move with different velocities, but the specific charge of all particles are same. So in general, if you write the equation of motion of a particle moving in electromagnetic field, what will be the equation of motion? Equation of motion of a charged particle moving in an electromagnetic field. We know this is actually F equal to m into dv by dt. Actually, this dv by dt is acceleration. And here, what is this F? F is actually Q times E plus V cross B. And this is known as Lorentz force. This force is known as Lorentz force. So, we can write the equation of motion of this single particle. This is not plasma particle, you can say this is a general equation. So we can write that m dv by dt is equal to Q into E plus V cross B. This is actually the equation of motion of a particle of mass m and charge q moving in an electromagnetic field. And from this equation, if we find the acceleration of the particle, that is dv by dt, then what will be this? This will be simply q over m into E plus V cross B. Say this is equation 1. Now, as I have told you just now, that we are considering the all the plasma particles have same specific charge q over m, although they can move with different velocities. So let this Q by M is same for all plasma particles. When you say plasma particle, it means plasma charged particles. And V1 is velocity of first particle. To get a general result, I am just considering the velocity of different particle is different. So this is velocity of first particle. You can say V2 is velocity of the second particle, and in this way you can say that this Vn is the velocity of nth particle. We consider that the plasma fluid contains n particles, n charged particles, and their velocities are V1, V2, V3 and so on up to Vn. So if we wish to write this equation of motion defined in equation 1 for all the particles separately, then what will be our equations? You can see, just you have to put at the place of V1, V2, V3, and remaining term will be all the other terms will remain same. So equation 1 for the different plasma particles. So we have dV1 by dt equal to Q by M E plus V1 cross B, dV2 by dt. This will be equal to Q by M E plus V2 cross B, and the nth term will be dVn by dt, and this will be Q by M E plus Vn cross B. Vn cross B. Now we add all these terms. So adding all these terms, we can write it as d dt V1 plus V2 plus so on plus Vn, and this will be equal to, see this term here, Q over M can be taken as a common factor, and when this E will be added in fact n times, what will be the result? This will be simply n times E, and plus in the second term we can take B as a common factor, and so the remaining term will be V1 plus V2 plus so on plus Vn cross B. When we will add all these terms, then this will be our result. Now here I am just going to define a velocity which is actually average velocity of the plasma particles. As you know, there are n plasma particles and their velocities are v1, v2, v3 and so on, vn. So the arithmetic mean of the velocity of these plasma particles will be simply the sum of the velocities of different particles divided by n. So if Vb, the average velocity, then what will be this V? This V will be actually equal to V1 plus V2 plus so on plus Vn divided by n. And from here you can see that the sum of all of these velocities, V1 plus V2 plus so on plus Vn will be equal to n into V. Now, this value of the sum of velocities of plasma particles, I am just putting in the above equation. See this equation. Here we will put actually n into V, and inside the square bracket again we will put n into V instead of V1 plus V2 plus so on. So what will be our result? So we will find that d dt n into V, this will be equal to q over m ne plus n into V cross B. And you can see this n is a constant, so it will be taken out from the operator, outside of the operator, and in LHS and LHS this n will be cancelled out. So this is simply dV by dt equal to q over m E plus V cross B. Remember, this was the equation number 1, but this is different. Here V represents the average velocity of the particles. So I have found the equation of motion in terms of the electric field vector and the magnetic field vector of the motion of plasma fluid moving in an electromagnetic field. Now, we will express this acceleration term, in fact, in terms of the space derivative and time derivative. So, how we will convert it? In general, you know that the velocity vector V in general is a function of a space coordinate and time. So now you can say this velocity V is actually equal to V of R and T, and equivalently we can say this is actually V of X, Y, Z, T. Here I have just considered that the velocity V is both space and time dependent. It does not depend only on time, only on a space coordinate, but on both. So in this condition, by the rules of partial differentiation, we can find the ordinary derivative of V, and therefore what will be this dV by dt? See here, as v is a function of 4 independent variables, so we will follow the partial differentiation. First of all, we will differentiate v with respect to x, and that will be del v by del x, and then as we have to find dv by dt, so this will be dx by dt, plus now with respect to y, the second term will be del v by del y dy by dt, and with respect to z, the third term will be del v by del z dz by dt. Now with respect to time, this will be del v by del t dt by dt. And you know what is this dx by dt? Actually this is x component of the velocity, and similarly this is y component of velocity v, this is z component of velocity v, and this dt is actually 1. So we can write this equation as this is vx del v by del x, this is vy del v by del y, this is vz del v by del z, and since dt is 1, so the last term is simply del v by del t. Now we can write the first three terms in this way. This is vx del x plus vy del y plus vz del z v, and plus del v by del t. Now in this bracket, the written quantity is not a physical quantity, but this is actually an operator, and you can write this operator as v dot del. I am just explaining why we can write this operator as v dot del. First of all, we write it and then I will explain it. So v dot del v and plus del v by del t. So what you see here, we have found that this acceleration dv by dt is actually equal to v dot del v plus del v by del t. So in equation number 2, we can replace the term dv by dt by these terms. So we can write equation 2 in the new form. In the new form can be written as this equation. We can write v dot del v plus del v by del t, and this is equal to q by m into e plus V cross B. Say this is equation 4. Actually, this equation 4 represents the momentum equation, but only when Lorentz force is present. If only Lorentz force is present, then this equation will be a momentum equation. But this is not a general momentum equation, as I have already mentioned before the derivation of momentum equation, the actual form of momentum equation, and you can see there are other terms in the RHS of that equation. But as I have told you earlier, that first of all we are just considering that our conducting plasma fluid is moving only in an electromagnetic field, or in other words you can say in this calculation we have just considered that only electromagnetic forces are acting on this plasma fluid, no other forces is acting. So if in an ideal situation, if there will be no other forces acting on this fluid, then this equation 4 will be called momentum equation. But in practice there are other mechanical forces acting on the plasma fluid. So to get the actual form of momentum equation, we must take into account all other forces. So you can say the few more terms in the RHS of this equation must be added, which are actually acting on the plasma fluid to get the actual form of the momentum equation. And as I have told you, the other forces are actually collision forces, pressure forces, and gravitational forces. So we will take all those forces, but this is momentum equation. You can say this is momentum equation only when Lorentz force is present. Lorentz force is present. But forces like collision force, pressure force, and gravitational force also act, or you can say also act on the plasma fluid so to get the actual momentum equation, we will account these mechanical forces. But in this lecture, I am just ending my lecture here. In the second lecture, I will discuss all these other three forces, that is collision force, gravitational force, and pressure force. And then you will get the exact form of the momentum equation.